Hello, everyone. Nice to welcome you to the VI Week. My name is Piotr Kruczkowski, and thank you for the opportunity to present to everybody. I am a software architect. I am working in National Instruments in the Integration Engineering Services team. Before I start, let me just ask if you can see what I'm presenting, if the content is okay, and if you can hear my voice. So maybe if you could reply in the chat window, I would be thankful for that. Okay, everything looks good on my side, so let me start presenting. Let me switch to my presentation screen. I hope everybody can see me and hear me correctly. So let's start. Functional programming inspired object-oriented template. Here with this presentation, what I wanted to do, what I wanted to present was not really the code itself, but rather I wanted to explain the decisions behind the design that inspired me to create that code, write that code in a specific way. So I kind of wanted to explain a little bit my functional programming journey, what I've learned, how that applies to object-oriented principles and object-oriented design patterns, how that applies to writing code that follows these principles, and what kind of lessons learned you can take from functional programming and translate them into LabVIEW. So this is what I wanted to present to you about. So I'm not going to do deep dives into the implementation of the template. I will link the template at the end, and the template is very nicely explained in the articles that I'm going to link you to. Rather, I wanted to explain what motivated me to create that template in a specific way. So what are my goals? I want to motivate everybody to learn and experiment with functional languages. I want to reinforce the existing best practices that we already have in LabVIEW and that are well documented, but I want to reinforce those. I want to provide a new perspective on data flow programming. And I want to share information about LabVIEW object-oriented template, the template that I'm going to link at the end. So a little bit about me. I've started using C++ about 15 years ago. 10 years ago, about that time, I got hired in National Instruments and I started using LabVIEW. 7 years ago, I started using Python and learned a lot about that. In Python, for the first time, I've learned about the concept of first-class functions, and I fell in love with that concept. Afterwards, I discovered functional programming, which is connected to that concept of first-class functions. After spending some time with Haskell as a functional programming language, which was fantastic, and I loved it, I switched to Clojure, which is another a little bit different functional programming language. And I've been learning Clojure for the last 2 years. In the community, you can find some of my libraries. I've created the user interface manager, the tree map API, and some other things for LabVIEW. And I started the Budapest LabVIEW user group. Yes, so the first topic that I wanted to mention and talk about is the misunderstanding related to object-oriented programming. And just let me make sure that everything is going smoothly with the recording. Yes, we are live. Everything should be okay, I hope. Okay, so the object-oriented programming misunderstanding. This was the first thing that really made me think when I started investigating and learning about functional languages, because there was this battle online, let's say, maybe not battle, but a discussion. What is the difference, and is functional programming compatible with object-oriented programming, or are they something fundamentally, incompatible with each other? So maybe, let me start a little bit about the object-oriented misunderstanding and a little bit about solid, and explain that a little bit. So what was the original point, let's say, of object-oriented programming, why it was invented in the first place? It is important to understand where it came from and what problem it was trying to solve. And then that allows us to understand a little bit better LabVIEW as a data flow language. So small memory and slow processing require low-level memory management and in-place modification. Historically, early on with the weak computers that we were using, small memory and slow processing required low-level interaction with the CPU and memory. So data processing and information flow was never really the driving force of object-oriented programming becoming a thing that people use. The need for object-oriented programming wasn't connected necessarily to data processing and information flow. Languages in those days were designed for the machine and not for humans. So humans, while trying to solve problems, they had to use the language basically that was given to them, the language that was defined for the machine, and we needed to learn that language and apply it to solve the problems. So we couldn't focus really on our problems. We needed to have very specialized individuals, very specialized programmers, and they needed to know the details about the machine. So you needed to know the architecture of the CPU, you needed to manage memory. You couldn't just focus on solving your problems. So there, to simplify these things and the problems that were arising in connection to those, object-oriented programming was invented as a memory access scope management. So the aim there was to protect against direct memory access in the global scope of the application. So when we had, the first application written in C, let's say, where the scope was global, essentially any part of the application could have modified the memory and the data located in any other part of the application. So the side effects of functions, let's call them, the side effects of functions were global. So the first point of object-oriented programming and this concept was to substantially limit this access to the global scope of the application, instead to enforce some kind of modularization of the scope of the application into these objects that you can only interact through encapsulated interfaces. So the problem here was that mutable state was everywhere. Still, the mutable state was the source of all evil. And the spaghetti by reference languages was caused by inability to understand which function is causing what side effects and when are those side effects happening. It's an interesting thing to think about that, or maybe a coincidence, that spaghetti in data flow diagrams that we see in LabVIEW is caused by the same issues. So people were calling, spaghetti code long before, or maybe in parallel to LabVIEW. It wasn't connected with LabVIEW wires looking like a spaghetti, but here, interestingly, the same analogy applies exactly correctly, also visually. So by-reference languages have a historical tendency to make code harder to write, harder to understand and debug and parallelize because of this global scope and because of the fact that a single function can change things in multiple places. And it's difficult to understand where these places are. Their nature encourages developers to couple modules. So the way how code in an object-oriented by-reference language is written encourages coupling. Actually, it makes it significantly easier and faster to write code in many languages if you are not following proper best practices and principles. And that is, well, it seems to be fundamentally backwards. It's easier to do things wrong than right. yet we are the people designing these languages. So maybe we should design a language in which, making the right choices is the thing that is promoted. So essentially, developers have the freedom to make arbitrary changes to the global state anywhere in the code. So you had to put rules on that development to limit that freedom. And the entire idea of object-oriented programming is an attempt to limit that freedom through encapsulation, exactly. So here, object-oriented programming by itself is not enough. You actually need more than that. So you need some principles, how you will modularize your code into these objects, right? So Solid was invented by Robert Martin, or collected together by Robert Martin, let's say. Uncle Bob, you might know him. These are the 5 principles that we should follow when we are designing an object-oriented application. Single responsibility, open-closed principle, list of substitution, interface segregation, and dependency inversion. I'm not going to go in detail through these principles because there's so many materials online that you can find about them. It's not necessary for me to explain them yet one more time. Instead, I wanted to focus on another thing. Object-oriented programming only mitigates the problem in by-reference languages, but it doesn't solve the problem because object-oriented programming doesn't come from an understanding what the problem actually is. What is the fundamental problem that we are trying to solve? And I will let you know in a second what the problem is. So it is very valuable to specify rules of modularity and polymorphism in a flawed world of by-reference object orientation. So by-reference object orientation still has problems, and it is very important to specify the rules of modularity in that world. So the solid principles give a very good guidance on generalities, but they say nothing about the information processing and the data flow in an application. So the reason Solid doesn't specify these remedies is because these specific remedies are historically difficult in by-reference languages. Like I said, it is difficult to implement in an object-oriented by-reference text-based language the best practices necessary to manage the flow of data. There are no smart memory management techniques in current compilers that can analyze the flow of data and decide when data is not needed anymore or when data needs to be copied. Right? By-reference code can adhere to all of the solid principles and still problems with correct, and it still can have problems with correct execution because the code being by reference and the passing of data by reference, that is the fundamental issue. So memory management and code modularity are orthogonal problems. They are not the same problem. They are different, separate problems, where the second one, the modularity of code, this is our job to solve as software architects. This is what our work is all about, translating the requirements into a modular code that is more easily maintainable in the future. But the first problem, memory management and the data flowing correctly in an application, that is something that we should be able to delegate to the computer. This shouldn't be our problem to solve, well, because we already have tools for that, right? Every language that has a runtime, like C# works on .NET, on a platform, let's say Java, works on the Java platform. So all of these languages are managed already. So why don't we give maybe a little bit more responsibility to the computer and inform it correctly how we need to manage that flow of data? Computer architecture should not force humans how to describe an algorithm. The architecture of the language and the architecture of the computer Well, maybe the architecture of the language, yes, should enable us to solve algorithms, but not the architecture of the computer. So here I wanted to mention about Alonzo Church. Alonzo Church was a mathematician living in the United States. He invented something called the Lambda Calculus, which is a universal notation expressing computation not tied to any computer architecture. So he worked with Alan Turing to define the world of modern computing. We are standing all on his shoulders, basically. His notation was so ahead of its time, it predated computers in the first place. So he created essentially the fundamentals of a universal programming language that predated the existence of computers. And 90 years later, there exist languages today which use his notation almost exactly. So that notation is Lambda Calculus, sometimes written as Greek Lambda Calculus. It is a formal system of mathematical logic. It is Turing complete. It can be applied in linguistics and in computer science, and it expresses computation based on function abstraction and application using value binding and substitution. I'm not going to go into detail on Lambda Calculus. I just wanted to highlight that it was let's say, a fundamental building block. Or the definition of Lambda Calculus was used later by John McCarthy, the computer scientist, who was the creator of the Lisp programming language. And the Lisp programming language here is one of the that family of languages. That's functional languages, and one of the functional languages. And his contribution to the field is very important. That's why I wanted to mention these two individuals, because learning about their life and learning about the things that they gave us gives you a very nice perspective of where can we go from here. I also wanted to mention another thing. So I want to talk about functional programming, and why is that? Well, it is very interesting. That when you look at the Wikipedia article for a comparison of programming languages, there is this nice table here which specifies, which functions are imperative, object-oriented, functional, procedural. And just out of curiosity, I was interested, what is LabVIEW here? What kind of paradigms does LabVIEW support? And it turns out that LabVIEW supports functional programming, which is very interesting because historically, before I've started learning about functional programming and what it is, I've kind of didn't know about it. I didn't realize that LabVIEW supports functional programming. I didn't even know what functional programming is. Well, I knew about object-oriented programming, and I knew that LabVIEW supports it. But what is this functional programming? So that's something that I want to explain because that's the thing that inspired the template, right? So before we go there, the same person who helped us and popularized the solid principles, so Robert Martin, Uncle Bob, he gave a presentation in 2014 talking about why we should all embrace functional programming. And it's interesting because he has a long history of being a C++ programmer, if I remember correctly. And he was, when he was writing his books about, clean code, for example, he was basing that on, I think, Java and C++. And yet he is promoting functional languages. And what he said was very interesting and important. So he said these broad statements: functional programs are simpler, which makes them easier to write and maintain. There are no temporal couplings, fewer concurrency issues, and there is no asking what is the state of the application, by reference state. Another presentation where I try to understand, what this functional programming is, said that it's difficult to define what functional programming means. It mentioned things like immutability. It mentioned things like pure functions, first-class functions, higher order functions. There's a lot of the word functions here used, but there's a couple of things that are, big on this list of associated words. So I've tried to come up with my own definition of what it might be. So what I came up with is this. So what is functional programming? It's declarative programming using function purity and mutability of data, where functions are also data, and the composition of first-class functions and data structures. So you compose data structures, first-class functions, you use the concept of function purity and immutability of data, and that is functional programming. So what do these things mean? So I highlighted these words in bold, so I'm going to explain what it means a little bit. Declarative means you say what things are instead of how to put them together. So you don't worry about maybe the sequential order of operations, but you rather care about what things are, that an individual function is a result of another function being called on some data, something like that. Functional programming can be done in many non-functional languages, non-functional officially, as long as they have support for certain features. So for example, Python, JavaScript, Lua script, these can do functional programming. And there's another list here: Haskell, ML, Erlang, F#, so functional programming on the C# platform, on the .NET platform, Scala. And there is this last one, which is Clojure, highlighted as because this is like a modern, very powerful Lisp implementation. So who uses functional programming nowadays? Well, it's Facebook, it's WhatsApp, it's Twitter. So big players already use functional languages. So what are these concepts? So let's start with purity. Purity means that a function depends only on its input values and its output, and it produces only its output values. It doesn't rely on any hidden inputs, and it doesn't rely on any side effects. So for people who are programming in LabVIEW, we have a certain advantage here already, because this is kind of the model that we've been using over the years. What we mean here by hidden inputs is, for example, reading something from a file. The contents of that file can change outside of the application. Somebody else can change the contents of a file. So they can be overwritten outside of our application. So if we depend on the contents of that file, well, we don't provide them as input values into our functions. We read the file, and that gives us some side effect, effectively, or some operation triggered by the user. We don't know if a user is gonna, well, we maybe know that a user is gonna click a button, but we don't know when that's gonna happen. So that's also a side effect of interacting with the world, interacting with the database, interacting with a file, with a hardware measurement device, also producing side effects. What does that mean? Well, the same thing, interacting with the world in some way. Triggering something to happen, writing to a file, writing something to the user interface. These things are not data transformations. They are rather things that happen in the world. And of course, we need those too. However, if we involve them in our application, and the deeper we involve them in our application, the more difficult it becomes to understand how that application works. So purity, output value only depends on the inputs and nothing else. So we keep less of the architecture in our mind at a time when we are creating our code in such a way. So we look at a function and understand what it does. Because it's just inputs and outputs, we understand what that function does. We limit the unknown inputs and side effects, and that makes our life easier. It is easier to distribute tasks in a team if every team member only needs to write a pure function. We can develop in increments. We can just add and add continuously pure functions, and as long as they are pure, there is no weird, strange behavior at a distance happening here. It's easier to reason about the code, to compose the code, to refactor, to test it. Taking a step back, looking at a complete application as a whole, our complete application can be just a collection of this pure data transformations, in a sense where each function is pure data transformation. So we can have multiples of these, and we just input into that flow of data, flow of information. We input the sources through sources, and we output through sinks. So what are sources here? Source is the entry point of the side effects driven by the outside world. So we get some data from the outside world, from the user terminals, files, a measurement device, database. Sinks are the opposite of that. Of course, we sync some data. So the output of our pure data flow program is synced to the user interface, to a file, or to a device that generates data. And transformations, and these are the biggest, the most important things, right? And there is the most of those, which is just pure data flow functions, working with the data from clusters, arrays, sets, maps, objects. And here, notice that the concept of data flow is not related in a sense to object-oriented programming. Objects can also flow by data because, right, when we say object-oriented programming, we don't mean by reference necessarily. Immutability. Here, there is a very nice quote that I found in one of the presentations. When it is not necessary to change, it is necessary not to change, right? And this this might seem obvious, yet it's not. Immutability. Once declared, a function or data never change. It's a major feature of most functional languages. It's a major feature of LabVIEW. This is something that is surprising to some people, that LabVIEW, by the nature of its data flow, actually supports immutability. No mutable state or references, or minimizing, because there are mechanisms where how we can create references and work with references in LabVIEW, but pure immutability in a language that supports really immutability for everything. There is no mutable state or references, no changes to the input arguments. We are only producing copies of the things that we need when we need them. So that means in an immutable application, there is no race conditions. There is no thread locks, because whenever you need something, you just make a copy of that and you're good. So it's a major feature of LabVIEW, and it's important to use it actually. So Darren Nattinger had this fantastic presentation a while back called brainless programming in LabVIEW. And in that presentation, he mentioned something that we shouldn't do. So we shouldn't be tied to the train tracks. If an object on our wire is not modified inside of a specific VI, so our function, that object should not be provided as an output, right? Because we are not modifying the original object that is passed in, rather we are producing some side effects with that object. We take its data and we produce some side effects, but we are not modifying the original object. There is no need for that original object to be output out of the function. So Darren encourages for us not to, be tied to the train tracks, because it doesn't make sense. And we actually lose a lot of the benefits that LabVIEW normally provides. For example, taking advantage of parallel execution. So this is exactly the concept here. When we are, making a wire copy of this object, we are effectively using immutability, right? We are not modifying by reference the object on that wire, as long as we are using proper techniques of data flow. So all of this code can safely execute in parallel. This is something that normally would not be possible in a typical by reference language. So pure and impure, there is a place for both, and we should use both pure and impure techniques in our applications. Many functional programming languages allow for impure functions. However, pure is always encouraged. Some languages enforce purity. Haskell, for example, enforces purity. So in the LabVIEW world, it would be like having two types of VIs. A VI that works with references and a VI that is a pure data transformation. And these, could look visually distinct in some way. We kind of have a mechanism like that with the in-place element structure. The in-place element structure allows for just that. Dereferencing a wire, working in inside of the in-place element structure, working by value, again, data flow, and then referencing that wire back out. All right, but this is an additional technique that breaks data flow. So it is actually encouraged not to use it as much as possible. Yeah, so when possible, separate pure functions and those with side effects. Use channel wires, queues, notifiers, but not direct memory access. Aggregate multiple effects and delegate them into a separate loop. Again, it's easy to create separate loops in LabVIEW because we have this concept of immutability, because data flow is built like that. We can create easily processing pipelines. We can work with buffered inputs. That is all relatively easy to do in LabVIEW. First class functions, that's another concept, and I'm going to speed up because I'm going to run out of time. Peter Norwig, who is or was, I'm not sure about that, but the director of research at Google, he demonstrated that 16 out of the 23 design patterns are simplified or unnecessary in languages like Lisp, languages in which the concept of a first-class function is used. And many object-oriented design patterns are expressible in functional programming terms. For example, the strategy pattern simply dictates a use of a higher order function, and a visitor pattern roughly corresponds to a fold. So I've seen a very interesting and funny presentation about that, a comparison of implementation of certain these design patterns and principles in an object-oriented language and a language that supports first-class functions, which LabVIEW unfortunately doesn't. That's why it's important to know about this. So in an object-oriented language, we have all of these principles and all of these patterns. And in a functional programming world that supports first-class functions, well, we have the functions. So it is significantly simpler and easier to think about certain things. So language design can and should drive towards a one correct and right solution. Because we are the designers of the languages, we can create languages however we need. The fewer techniques there are to do something right, the better, right? The less choices, patterns, mechanisms, paradigms you need to learn, the better. Because there should be a single easy way to do things. So LabVIEW unfortunately doesn't support first-class functions. Well, but maybe before we go there, LabVIEW doesn't support first-class functions, but there are techniques using object-oriented programming paradigms and design patterns to implement or mimic support for first-class functions. And this is one of the motivations behind the template that I've created. So another thing, higher order functions. Well, takes a higher order function, takes other functions as parameters. And a higher order function can also provide other functions as return values. So here, the concept of first-class functions is essentially we take a function, and that function travels in our application by value. So it uses immutability. We can pass the functions around in our application, not references to functions, the functions themselves. And that enables us very powerful techniques. So function that does either of these is called a higher order function. So here we see a function that accepts other functions or returns them is called a higher order function. It gives us, if you think about it, an instant dependency inversion in our design. So one of the principles of Solid and one of the patterns, the strategy pattern, is pretty much implemented automatically in a function that supports first-class functions and higher order functions. And many modern languages support higher order functions with input of lambda expressions, right? So you will see in other languages functions like map, reduce, filter, zip with, order by. These usually accept a lambda expression, which is nothing else but anonymous function passed in by value. So strategy pattern enables us to mimic that kind of implementation in LabVIEW. So strategy pattern would be, something like a generic filter that allows for additional specifications for what we should filter by. Right, so there is a generic filter that accepts some filter specifications, and these filter specification is provided as something, an object that flows by value into our filter function. So here you can see different filter specifications flowing in by value into our filter function. And with object-oriented polymorphism that we have available in LabVIEW and with dynamic dispatch, we can create effectively an object where we have, for filter specification, we have essentially just an interface that specifies a single function is satisfied. So it's kind of, we are creating a class that implements an interface that contains a single function. So that is pretty much, we want that single function to just flow by value in our design. Well, we cannot do that. So the next best thing is to create an object for it, right? But there is a lot of ceremony here. There is a lot of, I create a class. That class contains, a single function inside, and all of that just to enable dynamic dispatching and polymorphic behavior in our application. So maybe there is an easier way. Well, in LabVIEW there isn't, but I'm just saying in general, maybe there is an easier way. The template that I've created is, based on the strategy pattern, and it uses the strategy pattern in many places. So first-class function. Okay, one more time. What's the definition of those? Passing. When we can pass a function as argument to another function, or return them as value, or assign them as a variable in text languages, or store them in a data structure, again by value, well, then we have a first-class function support in our programming language. And this enables very powerful concepts like higher order functions, lambdas, closures, partial application, composing, piping, many things. If you notice, this is about first-class functions. Another article here. It's mentioned that well, these are the languages, a list of languages that support first-class functions. Unfortunately, LabVIEW is not on this list. And before you say VI server, yes, I know VI server, but that is by reference, and that is a very different thing. Yeah, so LabVIEW is not here, unfortunately. Right. So one of the concepts that we could use, partial application, is if we have our function, essentially, this object represents our single function, flowing by value, we can apply certain inputs to our function before it actually needs to be used. So we can, it's like specifying an argument for a function before you need to use that function. This is called a partial application. So it's a separation of the definition of what the inputs will be from when that function is supposed to execute. And that separation is, well, it seems trivial or simple as a concept, but it's actually a very powerful technique that allows very natural ways of composing functions. Well, we can do it with an object-based implementation here, with a class-based implementation. But we could theoretically use VI server to accomplish a similar thing. Notice here there is a function called add and multiply, and we are just passing both of them and applying some arguments to their inputs. And only after we've applied the arguments, we run those VIs, right? So that's kind of like a separation of when they are defined, when the arguments are applied, and when we are getting the result. These things are separated. That gives you a lot of power in a modular design. But yeah, don't use the second technique. If you want to use the first technique, right? So object orientation and strategy pattern. It is much safer because it's not by reference. Yeah, so I've made a video on or a comment on a video on YouTube, and a friend from YouTube very correctly described what is going on here. So design patterns are band-aids for the deficiencies of OP in by-reference languages. The main reason why a couple of the design patterns even exist in the first place is because functions aren't first-class members of these languages. So, which means functions aren't by value and immutable and flowing. So, to sum up, purity, immutability, and composition, where composition is direct support for easy function composition. Example, partial application, first-class function Dataflow, higher order functions. So purity, immutability, and composition equals Dataflow. So that's the reason why LabVIEW is specified in that list as a functional programming language, or a language that supports functional programming. We actually don't have all of these techniques with composition asterisk, right? We don't have certain mechanisms, techniques, features of the language that support a very easy composition. However, we have purity and we have immutability, and that seems that, well, that is good enough. But we can ask ourselves a question. This is just a theoretical, let's say, tangent. If we talk about Dataflow, does it need to be graphical? Well, looking at functional languages, functional text-based languages, we already see that it doesn't have to be only graphical. But there's a couple of interesting, tangents here that we can make. So from Kevlin Henney, very nice presentation about functional programming, things you already know. So he gave an example of looking at a standard, function call, where we call h on x and then g on h of x and then f on g of h of x. If these functions, if each of them are pure and the x is not by reference but by value, so there is immutability. So if these functions are pure and they are immutable and the x is immutable, then we can compose the functions in such a way where the function composition is independent from the value of x. So we can kind of prepare a complete data flow algorithm and not care at all what the value of x is and just run that complete data flow on x. And if you rewrite this a little bit, well, it turns out that it can look like this. And this line between the characters, that operator, is already used in Linux, for example. In Linux, this operator is called piping, and we can pipe a result of one function call in the command line. As long as it returns, data by value, and as long as it's pure, we can pipe the results of certain functions one into another and effectively achieve very complicated functionality just purely in the command line. If we talk also, I've been investigating or learning about Clojure for a while. It's a functional language. And the creator of Clojure, Rich Hickey, In many of his presentations, he uses the keyword Dataflow very frequently. In one of the presentations, even the language of the system, he was expressly talking about the data flow and imagining, like a production line on which things flow by value, and the data flow by value, and then you use queues. Queues rule you can see here on the slide. Decoupling producer and consumer. This is something that we teach in LabVIEW courses ourselves, and we've been living this, and here, the creator of a closure as a functional language says the same things. There's even a very funny article that I've read, or a very funny concept. Somebody is considering Microsoft Excel as a functional programming language. So there was a question, can Microsoft Excel be considered a functional programming language? And the answer, yes, absolutely. I claim that Excel is one of the world's most widely used functional languages. Not only that, it even has reactive semantics. The moment you change a cell, all of the other cells automatically update. And this is because, well, they said because each cell is fundamentally independent from another cell. And if we create a formula in a cell that depends on another cell somewhere, well, we are creating the formulas, but the formulas are pure. They don't modify, somewhere in memory, some value of X by reference. They operate purely by value. So if you think about it, LabVIEW as a language has kind of these two sides to it. It has the object-oriented, the solid, the modularity, the interfaces side, but it also has this functional side that many people don't notice. And if we notice it, and maybe if LabVIEW is given more features in the future that connected more closely to that functional side, well, we could embrace that a lot more than we do right now. And it's even interesting when you look at the Wikipedia article for Dataflow, you'll see Dataflow programming languages share some features of functional languages and were generally developed in order to bring some functional concepts to a language more suitable for numeric processing. Well, that's interesting. So the guidance for today, we don't have all of the features which might make our world much more functional, let's say, but some of them already we have in LabVIEW. Some of them are major features of LabVIEW. So what is the guidance? We should separate pure and impure functions, for example, by using queues or notifiers or maybe channel wires. We can limit the side effects to the edges of our design. And that's what we should do. We should really, read from input terminals, then do pure data processing, pure functions, and then output to some terminals that show to the user. But notice the side effects are limiting to the edges of our design, and that's what we should do. Do not do LabVIEW on Rails if you don't need to modify an object or that object, doesn't return new values, let's say, at the output. If you do nothing to an object, then just don't return the output value of the object. If you're producing side effects using that object, do not return the original object as the output. Let data flow guide your design. For modularity, use solid. It's still great. Of course it's great because it's an orthogonal problem to data flow. Solid and data flow do not conflict with each other at all. So what is great now? Object-oriented modularity is great. Interfaces added in LabVIEW 2020 are great. Higher order object-oriented patterns are great. By-value data flow is great. Channel wire and even the concept of channel wire is absolutely fantastic, and I love it. In the future, well, if we get a set of native higher order functions, and that would be really nice. If we get first class by value function support in LabVIEW, that would be very nice. If we could extend the LabVIEW as a language itself by having interfaces in the type system, that would be really nice. And if we had to write less syntax to make it all work, that would be also really nice. And all of that information that I just gave you feeds into this concept of the template. So the whole presentation was my motivation and what type of research was driving me to create this template. So now a little bit about the template at the end. What requirements I had for the implementation of the template? Well, I needed to wrap a device driver with an API for taking new types of measurements. So I needed to create here a measurement abstraction layer, let's say. The wrapper should be callable from test end. So I want to have a relatively short list of functions that I can call from test end. So, and each of these functions should fundamentally do something simple and quick and return a result. It should be extensible for easily adding new measurements using the same or new hardware types. So I kind of need like a hardware abstraction layer there. It should decouple modules and enable easy unit testing. Well, okay. It should allow for performance optimization of configuration, execution, and processing of the results. Okay, so I need to somehow be able to, be modular in the future and allow for adding new things, but also be able to optimize for performance. So that's a little bit, tricky. And it should allow for simulation and injection of test doubles or mock objects. Well, okay. Taking all of the lessons that I had and applying them to an object-oriented design in LabVIEW, well, I thought this. Maintainable code comes from separating where a function is defined, where its arguments are provided, where it is executed, and where it returns the results. If you enable this separation, you are on the right path. If you do not touch the world through side effects, so if you have no side effects in your application, your design should be pure. Results, algorithms, functions, configurations, etc. All of these types of things, so all of these classes, can be pure. And they can flow by value in your application, and they should flow by value. And only when you need to interact with the world using a side effect, only at that moment you should have a by reference class. So here we have just a high level view of how the template looks like. And you can notice here, there is a couple of things. The reference is separated from all of the other types of objects. And notice here, I have configurations, I have actions, I have results of those actions, and these three types of things, they flow by value, always, and that's it. So I can create new configurations, I can modify them, and it always flows by value. And then I can specify that configuration and store it in the internal memory of this reference that I'm interacting with here. And the same for actions and the same for results. So I have effectively configuration abstraction layer, action abstraction layer, result abstraction layer, and a hardware abstraction layer on top of that. So putting all of these abstraction layers together, that gives you the template. And what the references can be, well, they can be hardware, they can be a file, they can be a database. So whatever we are interacting with, the reference, that operates by reference, of course. The configurations, the generation, and the result operate by value. And that was a critical separation that we needed for our project, but I thought this is available. I can make this available, and this is valuable for the whole community. So I hope you will benefit from this template. I hope you benefited from this explanation. Please let me know if you have any questions. I will switch to the chat view for now, and hopefully I will be able to answer some things. Okay. Sorry about that. Let me just switch the presentation. Yes, new questions. Loud and clear works. Okay, I just see here for the audio. Great. Yes. First question is, when can we find the recordings after the session? Well, I am not 100% sure, but the recording will be definitely available, and the moment it is available, I will let you know. Or the system will actually let you know. I think it should be available through the same link that you used to join the meeting today. Yes, do I have experience with how well the G compiler sees that there is no future changes to a class wire? Well, that happens only locally. The moment, let's say, the moment an object wire enters into a function, this all happens by value. A copy is made essentially if you make a fork in the wire, right? So it happens locally. If you include some type of references inside of your class, or if you later somewhere in the application try to mutate, well, but I'm not even sure if that makes sense. You would need to create a by value reference to your object. That's an answer to Derek. Okay, let's go to the next question. How to estimate the overhead of using pure functions over classic functions? And that is related. Okay, so how to estimate the overhead of using pure functions, time for copying the data over classic approach with by reference value or using DVRs? That's a great question, and that depends very strongly on the design and the specific requirements that you have. I've been in situations in LabVIEW where copying was much more expensive than operating by reference. So I had objects that had 100 megabytes in memory, and I was forking that wire, and without realizing it, my application was behaving much more slowly than when I stopped, forking the wire and making a copy, because I just realized that, hey, that's a big object, so maybe I should force the compiler to actually use a reference here and operate in place. But that happens much less frequently than you would think, because most of the objects in our design are small. So copying them is very fast, relatively fast, and you gain many more benefits from following the principles of data flow for making your design much more easy to understand, easier to debug. The compiler also can optimize certain things if you work with data flow. So there is a lot of benefits of data flow that you never get when you are using by reference approach. And that was an answer to the question by Anonymous. And then another question, what is the difference between a function and the reference to a function when a function is a pure function? Okay, great question. That's again a question by Anonymous. What is the difference between a function and the reference to a function when the function is pure? And the answer is, if you have a reference to a function, you cannot effectively apply partial application. So having a reference to a function, and when you specify what the input arguments should be to that function, if it's by reference, then you are overriding the arguments that were specified previously. So kind of you need to have the concept of by value, and you need to have these functions flowing by value, because that allows you to independently specify arguments for multiple versions of the same function, let's say. Well, you can see it in the template if that answer wasn't clear enough. I hope it was. Another anonymous, does it mean that the functional programming is a silver bullet, or does it have its own problems and own patterns? Oh yeah, great question. Functional programming is not a silver bullet, in the sense of functional programming still doesn't protect you 100% from complications with side effects. And we are living in a world full of side effects. And these side effects are, you know, the whole point of the programs that we are creating. So let's say you interact with a database, and then somebody else interacts with that database, right? Well, you gain, you need to create somehow, you know, some transactions with that database to prevent race conditions or situations like that. So the moment a functional language, the moment functional programming has to interact with the real world, it cannot protect you from these problems of side effects on the outside, in a sense. So side effects are still a thing, and they are still a problem. Their influence is minimized in a functional language, but well, their influence still exists. It's just that you don't have as much of that influence in a functional language that is immutable. And yeah, I hope that was a good answer. So another question: what does it mean LabVIEW on Rails? Well, that means error cluster and object wire wired into every output and every input and every output of every function in your API. So going like you know, every method of your object, every method of your class having both the error cluster input and output and object wire input and output, even if they don't use them or don't modify that data. So we should only have inputs and outputs for the data that we actually interact with. That's kind of the point. Yes, another question from Anonymous. If I understand your proposal, do you suggest that we avoid by reference calls in our programs? I'm not saying avoid exactly. I'm saying understand exactly where these by reference calls are and try to limit them to the edges of your design. Only have them on the inputs and only have them at the outputs. Sorry, not inputs and outputs, edges. Input edge and output edge of your program, where the part in the middle is pure and by value. Okay, well, there's a lot of questions. Another question by Anonymous. Can you write the complete application with a functional language, or is FP more suitable for modules and APIs? That's a great question. Like I said, it's connected to the thing I said before. You need to have side effects, and you need to have side effects on the edges of your program. So you cannot effectively create a complete application by only using pure functions. So if you have a language that is a pure functional language, well, then you cannot make any side effects, and so your language is useless effectively. So you need to have both, actually. And that was the whole big deal with Haskell. You know, Haskell crowd for a long time trying to figure out how to have a really pure functional language and still interact with the world somehow. And that was a big question that they needed to solve. It's solved a little bit differently in languages like Clojure. Clojure just allows for functions to have side effects, you know. So there is no fancy technique that solves it. It encourages pure functions, but you can have side effects. And the same goes for LabVIEW. LabVIEW also encourages pure, but you can have side effects. Can you talk a bit about when you would start using pure functions as opposed to manipulating data via a more traditional way, action engine or functional global variable? That's a great question. And the answer is, how big is the data? If making a copy of that data is painful and expensive, don't make a copy of that data. Just work by reference. If instead the data is small and you can make a copy relatively for free, then you should do that and operate purely. So that was an answer to Jason. Okay. Okay. Yes. And question from John. Can LabVIEW 2020 interfaces be leveraged to help in some way? The answer is yes, absolutely. And the template that I'm sharing here uses them. So absolutely. And a question from Kabul. Great session. How is recursion managed, please? Well, that's a very interesting and specific question. So I feel like you have a little bit of insight into that. So recursion is managed, let's say, in a difficult way. LabVIEW has a very nice solution to that with our structures. So to our standard data flow, we added, LabVIEW has this concept of the for loop, for example, and while loop. All right, so you can use for loop and while loop and add shift registers on the edges. So you're you are enabled to pass data from one iteration of an algorithm to another iteration of the algorithm, but the algorithm inside can be a pure algorithm, right? So shift registers kind of work a little bit like data that you can mutate, but it's a single location, right? So, and it's a single location that makes sure that the previous iteration of your for loop finished before it starts another iteration of the for loop. So that is kind of, how this would be managed in LabVIEW. So you wouldn't implement recursive algorithms, but you would implement iterative algorithms instead. But yeah, in general, recursion is still a problem in some of the functional languages. Oh, okay. And that seems to me like I've answered all of the questions, or most of them. So thank you very much all for your time. Thank you for the opportunity to present today. I hope this was interesting, and I hope it's going to motivate you to look into the concept of functional languages more. And I hope it's going to motivate you to have a look at the template. Well, have a beautiful rest of the weekend. Have a beautiful Sunday, and hopefully see you soon. Bye.